Right. So yeah, welcome everyone. Week 3, lecture 2. So what we need to do today is just very quickly, in just about 5 minutes, wrap up this piece on DNS. I'll go over a few quiz questions just to make sure we're all on the same page when it comes to DNS. And then for the most of the lecture, I'll talk about P2P. We'll look at BitTorrent. We'll first we'll sort of compare file transfers over contrast how file transfers happen in client server versus how file transfers can happen over P2P, and sort of get a feel for why P2P is more scalable. Then we'll briefly talk about BitTorrent. Again, in the lecture, we'll kind of just be scratching the surface, just enough to give you a feel for BitTorrent. I have uploaded the full article, the original research paper that was written by Bram Cohen. So you can look that up. You don't need to for the purpose of the exam. Whatever we cover in the lecture is sufficient from the exam point of view. Then we'll talk about distributed hash tables a little bit, and then get into CDNs. And I'll kind of do a high-level summary of programming, sort of socket programming as well. Right. So one thing we spent quite a bit of time on DNS, of course. Last week there was we talked briefly about the security aspects. There was one attack I wanted to just elaborate on a little bit. So this is what's referred to as a man in the sorry, I'm confusing, a cache poisoning attack. So the way this could be launched is kind of depicted in this slide. So let's imagine I'm a bad guy, right? And let's say I have this domain, www.drevil.com, right? And as we discussed before, if I set up a domain, it is then my responsibility to either outsource the management of the authoritative name servers to someone else or set up my own. Let's imagine I've set up my own authoritative name servers. So when any DNS query comes in for www.drevil.com, my authoritative name server will provide the response, provide the IP address for my server that's hosting that particular web page. So imagine that someone, I set this up, I tell one of my friends, hey, can you visit my particular web page? And then let's say this is the response that is actually sent by my authoritative name server, right? So let's look at exactly what's happening. So of course, the query is for my domain, so that's straightforward. The answer section contains the IP address for my, that's the web server that's hosting this particular web page. So that's also fine. Down here, I'm providing information about the authoritative name servers that actually store this information. So this first one is all okay. I mean, that's kind of what you expect. A server called DNS1.drevil.com. Now, this is where things are getting tricky, right? So what have I done here? I'm claiming that this particular for this particular domain, this is the name server, right? Now, obviously here we have a problem. So I'm claiming that google.com, that's the name of my secondary name server, right? So this is my primary name server. And remember, we talked about how you at least want to have two, if not more. So in this case, I'm sort of suggesting that this is the name of my secondary name server. And then down here, I'm providing the additional information, which is effectively the IP address. I could provide the IP addresses of these two name servers. I've skipped the first one just for brevity. And here I'm providing the IP address for this secondary name server, right? Which I've indicated is going to be called google.com. And then I've said that is my particular the IP address for that particular name server. Now, Of course, note that this is a machine that's, let's imagine this is managed by me. Let's say I own this particular IP address space 129.45.212. So I've set up a separate machine here. I've set up a separate machine which has that particular IP address, right? Now, what is the problem here? So the problem is the local name server that sent out this query is going to cache all of this information, right? And it's going to cache this particular mapping, right? It's of course going to cache all of these as well, but this is the one we want to focus on. So this means any other machine on that particular network that is using that particular local DNS server, if they query for google.com, that local name server is going to say, hey, I've got a mapping already for google.com. This is the IP address, and that's what is going to be sent back to that particular client, right? So why is there a problem? Well, the problem is this is obviously not actually google.com. This is a machine that I, Dr. Evil, I'm hosting. So it's not actually the google.com domain that's being hosted here. So what I could do is on this machine, I could set up a page that looks just like your Google search engine. So when anyone on this network, when they get this mapping, they actually, let's say, open a browser, type in google.com, their local name server sends this IP address back, they set up a connection, and then when what they see in their browser, it happens to look exactly like google.com, right? Maybe it's gmail.com, let's just say, for the sake of argument. And then this person logs in, and which means I, Dr. E, will now have their Gmail login, right? So this is what's referred to as a poisoning attack, because what I've done is I've poisoned some other local DNS server with this incorrect information. This is incorrect information which I have created, right? I've wrongfully told someone that google.com maps to this when obviously it doesn't, right? So this was a known attack. There were many exploits back in the day that attackers launched using this sort of cunning technique. This, of course, is no longer possible because the way to get around this is simply not cache this information. Do not cache information about google.com. Why should you cache information about google.com that is being told to you by drevil.com, right? So the general rule is to only cache information if it is actually coming from authoritative name servers. So you can certainly cache this because this is the authoritative name server of Dr. Evil. It's coming from Dr. Evil. And if there was an IP address for this, you would be okay to cache that. But you shouldn't be caching information about google.com that's coming from drevil.com, right? You should cache information about google.com if it's actually coming from the Google authoritative name servers. So that's the normal practice, and that rule of thumb will avoid this sort of attacks. So yeah, I just wanted to sort of elaborate a little bit on this. Now there's a question, can flush DNS help in cleaning DNS poisonings? Well, it can, but you don't, I mean, the way to avoid this in the first place is to not cache information that's not coming from authoritative name sources. So you would never have wrong information cached to begin with, right? And all DNS servers will follow that rule these days. So these sort of attacks are no longer possible in practice. Right. Yeah, some last bits about DNS. This is more forward-looking, just to give you, just to make you aware that this is happening. So rather than, I mean, we've looked at how DNS works. Now there's a lot of push from all the browser designers to essentially integrate DNS with HTTP. So Chrome, Safari, all typical browsers these days have an extension called DNS over HTTP. I mean, the original idea was also to do it over TLS, and that still exists. So there are two separate standards now. You can actually, rather than use UDP, which obviously has security issues, you set up a TLS connection with the DNS server that's been queried and then send the query over that, right? So that ensures a level of security, which plain vanilla DNS does not. And the same can also be done over HTTPS, which obviously also runs on top of TLS, right? The benefit of this is this can be just managed by your browser. So effectively, when you type in a URL, your browser directly will send this query rather than invoking the DNS client on your machine, right? And there's a separate port essentially that is used for this. A lot of DNS resolvers support it. So particularly if you're using some of these open DNS resolver. DNS resolver here is just another term for the local DNS server that we were talking. It's also often called a DNS resolver. So if you're, rather than using your local ISP's DNS, local DNS server, if you were using one of the ones set up by Google or Cloudflare, they actually support this, right? So yeah, if you're interested, certainly look up. None of this is going to be on the exam. This was just more like to make you aware that these things are happening. So I think what we can do now is go over some quizzes just to cap off all this discussion on DNS. So if you could, in fact, this should be already active now. So if you could go to polev.com/Salil, that particular URL, and kindly answer this question. So it's asking you if a local DNS does not know where to find the address for a requested hostname, what does it do? Hope no one's picked A. Someone has, I thought so. Yeah, most of you are right. You would ask the root DNS server, right? There's no notion of a neighboring DNS server in DNS, if you recall, right? We had that hierarchy. So if the local DNS server doesn't know whom to ask, it always knows the IP addresses of the root DNS servers. So it can start off with the root, and then the root will point it to the appropriate TLD, and you move down that hierarchy that we saw earlier. Okay, how about this? So it's asking you which of the following are maintained by the client side ISP and the domain name owner. So the first, if you look at each answer, there's two things. So the first thing here refers to what's managed by the client side ISP. The second thing refers to what's managed by the domain name owner. Tim has commented about a cookie from Polev. Yeah, I mean, pretty much any site you visit will set up a cookie, right? So that's something we just have to live with, I guess. I mean, as long as you're following basic practices and not, I mean, most browsers will give you good flexibility over choosing what sort of cookies you're allowed to set. If you are very stringent, then certain things on the web may not work for you. So you kind of need to figure out what's the balance for yourself, right? Whether you want to be super strict and then forego of some services, or whether you're okay with a little bit of cookie junk. I don't know what to call it, whatever you call it. Cookie crumbs, yeah, that could be it. So let's look at your responses. So what is managed by the client side ISP, right? Let's first look at that. So if you again go back to some of those discussions, we said that each ISP will set up its a local DNS server. So any client that's on that ISP, whenever any application on it sends out a DNS query, that first gets sent to the local DNS server in that ISP. So the answer for the first part will be local DNS server. And then it's asking you the domain name owner, right? What is it responsible for within the whole DNS hierarchy? So remember again, if I'm a domain name owner, I have to then manage my authoritative name servers, because those are the name servers that have the exact answers for the web and maybe mail if you're providing both web and mail. So both of those servers. And so the authoritative name server will have the actual mappings, and that is my responsibility. So I could certainly outsource that to someone, which is quite common, or you set up your own authoritative DNS server, actually manage a machine which does that. Either way is fine, right? So the correct answer would be the third one, which again, most of you have picked. Remember, the root name servers are managed by ICANN. The TLD name servers are managed by different organizations depending on that particular TLD. Okay, let's move on to the next one. So it's saying, suppose you open an email program and send an email to, let's say, salil@unsw.edu.au. It's asking you your email program will trigger which type of DNS query. In the meantime, there's a question here. So going back to the cache poisoning example, how does a server know that a site it's referencing is authoritative name server? Yeah, that's a good question. So, but I mean, yeah, you've made a point with virtual hosting. It can be tricky, though. I think there's some additional records that we haven't looked at. There's a record which indicates who is the authority, right? So that very clearly states who is the actual authority for the domain. I think it's called a SOA record, source of authority or something like that. I forget the exact full form of that, but there are other records which can be used to gauge that information, right? Okay, this should be easier, I think. Let's have a look. Yeah, the answer would be MX, right? So because it's an email program. So remember we talked about type A is what we refer to as the typical www, the web browser mapping. So the correct answer would be MX. Well done. And then I think there's one more. This is going back to the point Tim made, actually, polev. So let's say you open a browser and type polev.com. It's asking you what are the minimum DNS requests which may be sent out by a local DNS server to obtain the corresponding IP address. So it's asking you to think of various scenarios. And in one particular scenario, the local DNS server would have to send out the least number of queries. So which one is it? It's obviously 42. That's the answer for everything in life. Of course, I'm joking. This annotation is blocking my view. How do I? Maybe I try this. No, that doesn't help. Yikes, it's a bad idea. Okay. Responses. So yeah, okay, so we got a varied response. So I would agree with the majority here, 0, because in the best case scenario, right, your local DNS server already has a mapping, right? So you opened your browser sends a query to your local DNS server. Now, the first thing your local DNS server does is it checks its local cache if it has a mapping already. And if it does, it will reply back with the IP address, right? So that's the best case scenario in a sense. So the correct answer would have to be 0, right? So yeah, well done again. Now, I think that's about it. Cool. So we can go back to, oops. We can go, yeah, we can now move forward to P2P. So that was all that we had to cover when it comes to DNS. So in the context of P2P, there's a question, if not cache, then 2 is right answer. Well, again, it could be anything, right? You could have a scenario where it could be 1, because in that case, what if it didn't have it cached locally, but what if it already knew who the authoritative name server for PolyV was? So it could then directly query that authoritative name server and get the mapping. So it could be 1, it could be 2. Really, you could think of all sorts of scenarios, essentially. Right? 42 would be probably unlikely. It would be hard to come up with a realistic scenario where you have to go through 42 name servers, but 1, 2, 3 could be reasonable, I think. Okay, so let's move on to P2P. And as the name, I mean, we kind of discussed this very broadly. Here we do not have any always on servers, and we essentially have arbitrary end systems talking to each other, essentially programs that are running on these arbitrary end systems which talk to each other. And the idea being that each of these peers is both requesting service and providing service. And this service could really be anything. It depends on the particular application, right? So as noted here, the simplest example that we are all aware of is, of course, file sharing, BitTorrent. I'm sure all of you only use BitTorrent for legal downloads, right? No one is downloading anything illegal over BitTorrent. And then there are other applications. There's a streaming service called CanCan. Skype originally was P2P. Since Microsoft bought it, they've kind of pivoted a bit. So I wouldn't really, maybe I should remove Skype really. It's not, I mean, there are some aspects to it that use P2P. So fair enough. And then there's all this blockchain, interest in blockchain that's coming up, right? So cryptocurrencies, all blockchains essentially use P2P model, right? So the good thing about P2P is that it's self-scaling, because each peer that you introduce in the network is not only increasing the load, but it's also increasing the capacity, right? Because each peer essentially is providing service, right? So in BitTorrent, for example, if you're participating in a file sharing scenario, you're downloading the file and at the same time, you're also uploading the file, right? So that's a good thing. That's the really positive thing about P2P networks, that they're self-scaling. So you're not sort of restricted with having these servers, and then you're tied to the limitations of how the server can service the requests. At the same time, it's not all free lunch. The downside is that peers may keep getting disconnected, right? So you can't be guaranteed that peers will stay on the network all the time, which means you need ways to manage this dynamic network, because effectively this is a dynamic network. A peer may suddenly drop off, a new peer may join, the same peer may connect through a different IP address and stuff like that, right? So we need mechanisms to deal with that. Now, one terminology you might also hear is this term overlay. So this is often a term that's also used in P2P networks, because what we are essentially doing is we are overlaying a network on top of the underlying internet, right? I mean, from the perspective of the application, if you look at it from the application point of view, it is as if, for example, here we have created this 3-node overlay network on top of the internet, right? Where this is one node, that's another node, this is a third node. Now, of course, these nodes are not necessarily directly connected to each other. They go through various routers, switches. So this path is not a direct path as such, right? It's overlaid on top of the internet. So you might sometimes see this term overlay networks also used. Okay, so now let's first, in this journey of P2P, let's first compare and contrast why P2P is actually scalable. So to do that, we'll consider a very simple scenario. We'll consider a scenario where we need to distribute a file of size F. And in the first instance, we'll look at client server, then we'll look at P2P. So let's start with client server. So here we assume that the file is initially stored at the server. The server upload capacity is US. We have N clients. The upload capacity of each client, or the uplink capacity is U1 up to UN. Downlink capacity is D1 up to DN, right? And we assume that in this particular instance, there's no one else is using, I mean, the internet has sufficient bandwidth and there are no other applications running on these devices and so on and so forth. So we are just focusing on this file transfer effectively, right? So we'll assume that the server services the file sequentially. So since we have N clients, each of those clients must obtain a copy of the file from the server, one after the other. And the time to upload one file is effectively F divided by US. That's the upload rate of the server. And since we have N files, the total time to upload collectively all N files will be N times F by US. Now, from the perspective of the client, each client will basically need F divided by DI, right? So that's the time to download the file from the perspective of each client. And amongst these clients, let's imagine there's one particular client, we don't care which one, but there's one particular client which has the lowest download capacity among all these clients, right? Maybe they're on a slow network or whatever. So from the perspective of the client, that particular client is going to take the longest amongst all the clients. So the download time for that client will be F divided by D min, right? So in terms of the how long does it take, right? So what's the lower bound essentially to distribute the file amongst the N peers, N clients in this case? There's no notion of a peer really here. So it's either going to be that or it's going to be that, whichever is the greater value amongst these two, right? Whichever is higher will be the absolute lower bound for distributing the file to the L clients using a client server approach, right? Now note here that only one of those terms is dependent on N, right? N is the total number of clients here. So as the number of clients start to increase, this term will most certainly be greater than this, right? And which will be relevant when we are doing the comparison, because what we want to see is as we start increasing the clients, which one is more scalable? Is client server more scalable or is P2P more scalable? So now let's contrast this with P2P, right? So here again, there are some assumptions we are making. The assumption is initially the file is stored at the server, right? So initially the file is sitting here. And of course, the other peers are the one who are trying to get this file. So at the minimum, the server has to upload one copy, right? That's the absolute minimum, right? The server has to be able to upload one copy so that the file can then exist in the network and the others can then start sharing it with each other, right? So from the server's perspective, it needs to send at least one copy, and the time to do that would be F divided by US. From the perspective of the clients, things don't change. It's still from each client needs to get one copy of the file, and the time to download the file would be again F divided by DI. And just like in the previous slide, we'll assume there's one particular client which has the lowest bandwidth, dmin. So the minimum time, from the perspective of the client, the longest it takes to get the file would be F by dmin, right? So these two terms are hopefully fairly straightforward. Now, one thing we do need to consider in P2P is the aggregate view of the entire network, right? Because this is a P2P network, so which means each of those peers needs to get a copy of the file. And which means collectively, we need to be able to upload that much data into the network, right? Because each client needs a copy of the file. And then if you look at the total upload capacity as a whole, right? Who's uploading this? Well, everyone is uploading this, right? So the max upload rate would be US, that's the capacity of the server, plus the individual upload rates of each of the clients. So this is a summation over N, right? The total number of users in peers in the network, right? So from the perspective of the collective network, we also need to consider this delay, right? So the total amount of data uploaded and then the total upload capacity of the network. So here we now have three terms, and whichever one of this is the largest will determine the lower bound, right? Remember, this is just a bound. In order to actually achieve the exact value as noted here, for example, we would need to design an actual protocol. And I think if you think about it, the only way to achieve this would be as soon as each peer gets a bit, it immediately uploads it. So this may a bit unrealistic, but we are just looking at a bound, so it's fine to consider this. It may be very hard to actually design a practical protocol that meets this bound, but let's not bother about that for now. There's a question why clients need to upload the file, because it's a P2P network, right? So we say collectively, right, we need that much amount of data to be uploaded, and collectively all of them are involved in upload, right? Because each peer is not only downloading, but also uploading. So the total upload capacity of the network is the total upload capacity of all the nodes that you see, right? So yeah, of course, the assumption here is everyone is downloading the file, right, and uploading the file. So Patrick is asking, is the client automatically uploading file? So yeah, as I said, we are not concerned about the precise protocol, right, to achieve these bounds. We are just looking at it from the perspective of the bound. In the previous case, the clients do not upload. Yes, of course, in the previous case, it's only the server that's uploading the file, right? They're just downloading from the server. So if you look at this, again, here, you'll notice there is only one term really that depends on N, right? Which is going to be this particular term, right? These two are not dependent on N. So as N starts to increase, you'll see that this term will be much greater than these two, right? There's a question on which is better. Well, that's exactly what we are getting at in the next slide, right? So the whole point of doing this was to compare these values essentially, right? And to give you a feel for why P2P is more scalable. And that is precisely done in this slide. So here we have assumed certain numbers because in order to draw a real graph, you would need certain numbers. So these are some of the numbers used. Again, this is not super interesting. What's interesting is the shape of these curves, right? So if you look at client server, you'll see it linearly increases, which is what we expect, right? In this case, as N increases, this linearly increases. However, if you look at P2P, of course, as n increases, the numerator here is increasing, but even this is increasing, right? Because each peer you add into the network is also adding its own upload capacity, right? So in fact, in P2P, as n increases, both the numerator and denominator increase. And you'll see that that results in the sort of flattening of that curve, which is precisely what you see here, right? So of course, initially it will increase, but once you get to a certain point, adding more peers doesn't really harm the delay, right? Because each peer is introducing its own capacity, upload capacity to the network, right? So yeah, that's a sort of illustration that as n increases, right, this can get very large. Mind you, again, as I said, this is just a theoretical limit. In practice, if you wanted to achieve this limit, particularly in the P2P context, it would be a little tricky to design a practical protocol. That said, you could potentially design practical protocols that may be slightly greater, but are still significantly lower than the client server model. Is this logarithmic? No, I don't think this is logarithmic scale, right? This is a linear scale. Yeah. Okay. So that was just to get a feel for why P2P is scalable. Now let's move on to BitTorrent, right? As I already hinted, I've put the entire paper on the website. In fact, there's a lot of resources you can find under the lab. Page. Oh, sorry, on the lectures page, right? So if you look here, you'll see that typically you'll always find a lot of stuff, a lot of web links that I might show, some that I may have missed. So you can always have a look through some of this. So yeah, this is the original article from Bram Cohen. So if you're interested, certainly look it up. You don't need to from the perspective of the exam. A couple of questions. The growth of P2P, is it logarithmic? No, not really, right? It flattens off. This is not a log. This wouldn't be, log would probably be still growing, right? This is practically saturating here. So this is not really logarithmic. Is min distribution time the download rate? Yes, the time to download the file. Not rate, it's the time, right? It's the time to distribute the file. Okay, so let's look at BitTorrent. Again, I'll kind of just give you a high level view. So the idea here is to break up the file into chunks and then to get all the nodes that are involved in the download, distribute these chunks to each other, right? So that's how we achieve this scalability that we saw, right? So in practice, like if you really wanted to meet this bound, as I said, you would probably need a protocol which as soon as one bit arrives, the client should be uploading that bit. In practice, that's hard. So typically you break it up into chunks, right? So rather than uploading one bit at a time, you break up the file into chunks and then upload and download at the granularity of chunks. So by default, BitTorrent uses 256 kilobit chunks. When you are uploading the file, the first thing you do is you divide up the file into those chunks. It also runs a hash on all those chunks. So when you download the torrent file, it will contain information about how many chunks there are and the hashes of all those chunks. Now, why? Well, because we want to make sure we are not downloading garbage chunks, right? Because someone might suddenly, you might have a malicious entity who might create a file that looks like the original file, but is just corrupted and sort of wasting people's time, right? So that's the reason we have these hashes. So each time a chunk is downloaded, the client would take a hash of it and check against the hash values in the torrent file, right? Anyway, so yeah, so the idea is peers just distribute, send and receive these chunks. All the peers that are participating in a particular file exchange are referred to as a swarm, like a swarm of bees, right? And there's a now with systems like BitTorrent, we do need some infrastructure. We can't get around that because we need to have a way whereby we are tracking all the peers that are actually active, right? Because when someone new joins, how do they know who to join with, who are the other peers, right? So we do need this infrastructure node, which is called a tracker, that is keeping track of all the current peers. So these peers are constantly, I presume there's some protocol here, at a certain frequency, they need to keep telling the tracker that they're still alive and participating, right? And based on that, the tracker will essentially have a list of IP addresses of all the peers that are participating. So when a new peer joins, they can be told of who are the other peers in the network. So let's say Alice joins, Alice would get a list of peers, maybe not all peers, maybe a subset of the peers, and then Alice will set up TCP connections with each of those peers and then start the file exchange process. Now, again, BitTorrent uses TCP simply because TCP provides guarantee that all the data that's transmitted is received. So then BitTorrent doesn't have to worry about reliability, right? As long as it's using TCP, it knows that each chunk that's sent across will be delivered to the other peer, right? There's a few questions. Chunks may be downloaded non-sequentially. Does the list of hashes also inform how to rebuild the file correctly? Yeah, so all that information will be in the tracker, right? So essentially you have a list of chunks, a list of peers, and there'll be some numbering, essentially sequence numbering, which will allow a peer to sort of group the chunks in the correct order, right? There's a question about IP address hashed or are they public? I think that depends on how the tracker is implemented, I guess. So I think I don't use BitTorrent that much, frankly, but I haven't looked at that. But yeah, that's something you could look up as to how exactly are the IP addresses stored, right? So infrastructure node is centralized. So yeah, that is one issue, right? And when we talk about DHTs, we'll talk about the way to get around this. But this is a problem in that you have to have this bootstrapping node, right? So there's a way to distribute this functionality as well, which is typically done using DHTs. So we'll look at that in the later part of the course. Oh, sorry, in the later part of this slide set itself, right? So what does the torrent file contain? Yeah, it contains the IP addresses, essentially, of all the peers, the list of file chunks, the cryptographic hashes, and sort of information about how to rebuild it. So the peer joining the torrent initially will set up these TCP connections with all the other peers. Now, mind you, the neighbor set that a peer has will also be dynamic, right? So because it's not guaranteed that these peers will be alive for the entire duration that Alice is downloading the file. So some of them may go away, right? They may jump off, they may shut down the application or whatever. So Alice may need to set up new connections with some of the other peers that were obtained from the tracker. So this set of neighbors is not necessarily fixed. It can keep changing, right? Depending on, I mean, there's no control really. This peer cannot control what the other peer is doing, right? So it can be dynamic, quite dynamic in certain instances. Now, when a peer joins, obviously, if Alice has just joined, she's not going to have any chunks because you start off with nothing, right? So eventually, as you'll see later, she'll get a few chunks from some of the other peers, and then she can sort of start exchanging these chunks. So what happens is each peer will send the other peer its list of chunks. So in that, you can imagine there's some sort of map which keeps track of all the chunks, and then you could imagine there's a entry, there's a 1 for if the peer has a chunk, a 0 if it doesn't, some sort of data structure you could envision, right? That's keeping track of all the current chunks. So these peers will keep exchanging their chunk map, essentially telling each other what chunks they have. And then the question is, okay, how, based on that information, how does Alice or any peer effectively choose which chunks it needs to download, right? Because it's got a bunch of neighbors. They've told Alice, these are the chunks they have. Now, of course, if Alice already has those chunks, she wouldn't request them. But for the chunks that they do not, Alice does not have, she'll need to figure out which chunks she should get first. So what BitTorrent does is it uses this concept of rarest first. So which means it tries to get copies of the chunks which amongst her neighbors has the least replicas, right? So let me give you a simple scenario. So imagine in the context of Alice, we have Bob, Chris, and David as 3 neighbors, or maybe Bob, Christine, and David. So let's say Bob has chunk 1, doesn't have chunk 2, doesn't have chunk 3, right? Imagine Christina has chunk 1, chunk 2, doesn't have chunk 3. And then David doesn't have this, doesn't have this, and David doesn't have anything, let's just say, for the sake of this discussion. So if you look at these 3 chunks, which is the rarest? So obviously the third chunk doesn't exist, so let's just ignore that. The second chunk, there's only 1 copy. The first chunk, there are 2 copies. So in this case, the second chunk is the rarest chunk, right? So that's what we mean by rarest first, essentially, right? So you try to, the idea being you try to sort of equalize the replicas of the chunks across the entire chunk set, right? So that's the reason the policy followed by BitTorrent is to request for the rarest chunk first. In terms of sending the chunks, what BitTorrent does is it uses this notion of tit for tat, right? So imagine Alice. So Alice has a bunch of peers. Each of those peers has requested certain chunks from Alice based on this rarest first idea. Now Alice needs to decide which of those requests it's going to service, right? It can't service all. It needs to pick a few. So how does Alice do that? So what BitTorrent does is it's actually very clever. So what it does is it will send chunks to 4 other peers who are currently sending Alice chunks at the highest rate. So it's like, if you send me chunks at a good rate, I will send you chunks in return, right? So that's the mentality. Essentially, you're trying to match up peers in terms of their upload capacities, essentially, right? So that's kind of depicted in, or maybe let me go through this slide and I'll come to that, right? So that's the idea. You try to sort of match up with neighbors. So that's why it's called tit for tat. And the way each peer does that is every 10 seconds, it measures the data rate that other peers who are uploading to it are currently uploading chunks at. So it will then come up with an ordered list, and then it will select the top 4 in that list and say, hey, if you've requested any peers chunks from me, I'll sort of give you those particular chunks right now, because you're in turn giving me chunks at a very high rate, right? And it keeps doing this every 10 seconds, essentially. And this list obviously could change, right, depending on what the other peers are doing. However, you might think, okay, if that's the case, how does a new peer get chunks in the first place? Because if a new peer doesn't have chunks, it's obviously not going to be uploading chunks. So it's never going to feature in this top 4 list of any other peers, because it doesn't have anything to send in the first place, right? So in order to get around that, what BitTorrent also does is every 30 seconds, each peer will just randomly select any other peer it's connected to and which has requested chunks, and start sending it chunks. So for those randomly chosen peers, we don't care about the rate at which they're uploading data. In fact, they may not even be uploading data. That's the whole idea, right? That when Alice comes up, one of its peers will randomly choose it and give it a few chunks by following this particular protocol, which is called optimistically unchoke, right? So since Alice is only uploading data to 4 peers at any time, the others are referred to as being choked. And every 30 seconds, Alice would just pick anyone randomly and provide a few chunks that were requested, right? So the idea is that when, let's say in this scenario, Alice optimistically unchoked Bob, once Bob receives some peers in this manner from Alice, Bob may also receive some chunks from the other peers in this same fashion through the optimistic unchoke part of the protocol. And then since Alice gave Bob some peers, Bob in return will match the favor and give Alice some peers, and Bob will then become one of Alice's top 4 peers, and Alice in turn will become one of Bob's top 4 peer providers. So that's the idea. You try to sort of match up to neighboring peers if they have sort of matching upload rates, right? So that's sort of the high level idea here. Yeah, and as I said, you can read up a lot more in the actual paper if you're interested. From an exam perspective, I won't ask you anything beyond what we've covered. So let's look at some questions. So do the chunks include headers? Well, yeah, so BitTorrent would have some headers, right? So if you look at the actual protocol, I'm sure they will have to have certain headers that so the chunk is only the data, but then when a peer gets a chunk, it might need, for example, what is the chunk ID, right? And stuff like that. So certainly there will be certain headers introduced by BitTorrent. And then of course, since it's going and sitting inside a TCP segment, there would also be TCP headers like Tim mentioned here. Are 4 peers in the same top 4 group, or can each peer have a different top 4 group? Yeah, I mean, this can be dynamic, right? I mean, the idea is to try to match 2 peers up for a little while. I mean, it's very hard to have a long lasting matchup, I guess. So all of this is quite dynamic and fluid, right? Because peers go, peers come by. You might reach a point where these 2 peers now have exchanged all the chunks each other had basically, and now they're looking for chunks which neither of them have, right? So then they may not necessarily feature in each other's top 4 list anymore, right? What happens when there's 0 peers? Well, yeah, I mean, this is a classical problem with P2P, right? If you reach a state where you're missing certain chunks and you don't have any peer online which has those chunks, well, too bad, then you're stuck, right? There's nothing that can be done because this is completely voluntary, right? You cannot force someone to be online and participating. So that is the issue with P2P, right? Ensuring, addressing problems like that, right? Okay. Right, where are we in terms of time? Okay, maybe this might, or maybe let me just push on a little bit. I'll take a break after DHT because that will conclude the P2P part, right? So one question we kind of alluded to earlier was the existence of this tracker, right? So we said, okay, in order for BitTorrent to work, we need this tracker. And this currently, the way this was described, it was a single sort of server that's managing all these peers and keeping track of them. Well, now the question is, can we actually distribute the tracker functionality itself, right? So rather than have one dedicated server managing it, can we actually distribute the tracker across multiple nodes? And that is precisely what can be, that is precisely what DHTs can be used for, right? Of course, it can also be used for various other things. So what is a DHT? Well, it's just a distributed database effectively, right? In fact, let me jump ahead. So a hash table is something like that, right? So in a hash table, you have certain key value pairs. So examples could be, say, the name and the phone number. So effectively, the key is what you search for. So let's say you're trying to look up phone numbers. You send the name, and then you receive the value, right? So this is effectively what is a database, and the idea is to break up this database. Firstly, the way we organize this is through hash functions. So we pass the key through a hash function that gives us a certain value, which allows us to index into the database, right? So rather than searching for the actual key, we hash it and then look up that hash value, right? And once we have the entry, we go and extract out the value, right? Now, of course, you can do this in a centralized manner, no harm in that. But what we are really interested in is breaking up this into smaller chunks and distributing parts of this database across multiple nodes, right? So in the context of that tracker, you could imagine the key would be the file name. So let's say you're downloading a particular movie. Oh no, that's illegal. Let's say you're downloading a particular Linux distro, right? Which is perfectly legal. So that would be the file name. And then the value would be the IP addresses of the peers that are currently in that swarm that are exchanging that particular Linux distro with each other, right? But of course, you could use it for other things, like a key could be a tax file number, the value could be the name of the human or whatever. Doesn't matter. I mean, from our perspective, we just assume there's a key value pair. And then what we want to do is distribute these key value pairs over multiple peers rather than storing it in one server. And the typical APIs we expect is to have a way for someone to query. So a peer can query for a particular key. And then in return for that query, the network would say, hey, this particular peer has the key value pair that you're looking for, and give you the, say, the ID of that particular peer. So then you could go and fetch that particular value from that peer, right? Similarly, we could expect an API that allows us to insert key value pairs. So let's say you're adding a new entry, right? In that case, again, you send the insert command, and then the network tells you, hey, this is the particular node that is going to store this particular key value pair. And then you can actually go and put that key value pair in that particular node, right? So the question then is, how do you set this up, right? How do you assign, who decides what keys should go to which peer? So one easy way to do that is essentially use integers. So we assume the peers themselves have some integer IDs. So this could be, for example, you could hash their IP addresses or something like that, right? And then the keys that you're searching for also need to be hashed to that same integer range effectively. So let's say a range from 0 to 16, 0 to 15, for example, right? And then the key value pair will be stored in the peer that is closest to the actual hash value of the key. So I think this can be better described using some examples, which I have on the next few slides. So as it says here, each peer has an identifier, which goes from, say, 0 to the power n minus 1. So effectively, we are using n bits as the ID, right? So for example, if n was 4, we would have a range of 0 to 15, right? And 4-bit identifiers for each peer. And similarly, the key would also be mapped to this same range. So you would pass the key through a hash function, and the output of that would also be in the same range, 0 to 15, right? So then the question is, not all peers may be alive at a given time. So some of the peers may be online at a particular time. So based on that, based on the current peers that are active, where should a particular key value pair reside? So the rule of thumb is fairly simple. You store the key in the peer that has the closest ID to the actual ID of that key. So as an example, let's imagine we are using a integer range 0 to 16 for both the peer IDs and the key IDs, right? And let's say at a current time, those many peers are currently active on the network, right? So we have what, 1, 2, 3, 4, 5, 6, so 8 peers are currently active, and those are the IDs of those peers. And let's say we want to insert a particular key value pair, and let's say the key maps to 13, right? So now if node 13 was actually online, then obviously this key would be stored in node 13, but node 13 is not online. So now where should it be stored? So the rule of thumb is to store it in the successor, the closest, right? So by closest, we mean the one that's immediately after, essentially. So it could, in this case, it would have been 14, right? If 14 was not active, then who? Then you would go back to 1. So you kind of, at the end, you go back and restart, right? So that's the idea. So for example, key 15. Now there's no node 15. So who's the successor? It would be 1. We assume a circular sort of logic here, right? So now the question is, okay, how do you actually structure the network itself, right? So we have these nodes that are alive. How do you structure the network? So in the most naive sense, you could say each peer is aware of every other peer, right? So imagine we have 4 peers alive, just to keep the drawing a bit simple. So you could imagine a network where each peer has a connection to every other peer, like that, right? So a fully connected network. Now, the problem with this is this will not scale. I mean, it's fine for small networks like that, but imagine if you had 100, 200 nodes, 1,000 nodes, then it clearly doesn't scale. So a very common way to organize a DHT is to have a circular topology like that. So in this case, each peer is aware of its next and previous node, and then you simply connect all the peers as a circle. And then the assumption is typically that queries only propagate in the clockwise direction, right? So something like that. So in this case, each peer is effectively maintaining 2 neighbors. So the next node and the previous node. And in the worst case, let's say you want to query this. So let's say peer 1 wants to know where a particular key value pair is stored. So in the worst case, the query would have to propagate all the way to node 15, right? So imagine it was searching for key value pair 15 or 14, let's just say, right? So in this case, it would sort of query along that circular network like that. 14 would now be located at 15 because that's the immediate successor, and 15 is going to say, hey, I have it, and then 3 can go and fetch it from that. So in the worst case, in this sort of network, you would need to send n messages. Then sort of messages go all the way across the network. And on average, you would need to have n by 2 messages, right? Now you could save on that by having certain extra connections. So there's this whole notion of shortcuts. So here you'll notice each node is now keeping track of 3 nodes. So the next node, the previous node, and 1 additional shortcut like that, right? So this could allow you, so 3 has a shortcut to 8, 8 has a shortcut to 15, and so on and so forth, right? So this could actually save the number of messages that you need to send to query. So for example, that same example that you saw earlier, you just need 2 messages, right? So on average, you're cutting down the number of messages to order log n in this case, right? So it's a trade-off essentially. How much extra information should each node keep? And that does save the number of queries that need to be sent. Now, one issue with networks like this is, what do you do when a node dies, right? I mean, for various reasons, a node may die. So node 5, for example, may die. Now what do we do, right? So if a node dies, we need a way for 4 to figure out that it should now connect to 8. So normally each node would not only keep track of its next and previous node, but the second successor as well, simply to deal with this issue of peer churn, right? So if this node dies, then 4 is aware of the next hop. So it can establish a connection with 8. It can also discover node 10, and then everything is fine, right? The other issue is what happens to the key value pairs actually stored on a node, right? So you need some sort of redundancy to manage that. Otherwise, you would lose those key value pairs, right? So there are various heuristics on how you manage that redundancy, right? So you need at least another node to have a copy of the key value pairs, right? So yeah, there's a lot to this beyond what we've covered. I mean, how do nodes join, how much state and all this. So again, most of this is out of scope. So from the point of view of the exam, I'll only ask you stuff that's on the slides, but I have again linked up to the original paper, CORD. So you can certainly read that up in your own time. So let's look at some questions. So does it distribute to every online torrent users? I'm not sure what that actually means. DHT poisoning, I'm not sure what again that means. This has nothing to do with DNS poisoning if you're confusing with that. I mean, here we are talking of storing key value pairs. I'm not sure what you mean by poisoning. Does it use a distributed tree structure database? Again, for what? Which part? I'm not sure. How does it know to take a shortcut? Yeah, so that would depend on the query, right? So for example, here 3 knows it has a shortcut to 4 and 8, and it knows it's looking for 14. So it knows 14 is closer to 8 than 4. So it would then send the query to 8. If it was a query for 4, then it would send it to 4 because it was closer, right? So it basically compares the key it's looking for with the IDs of the shortcuts it has. And based on that, it can send it to the one that's closer to the key that it's being searched, right? Would a malicious actor be able to break the network? Yeah, certainly. I mean, all of this assumes nodes are behaving as expected, right? So as soon as you start thinking of malicious intents, most of these concepts may break. Again, you would need to add that layer of security on top of this. This is all assuming all nodes are behaving as expected, right? Okay, the question was about directing peers to the wrong file. Yeah, so again, sort of repeating what I just said. So the assumption here is all peers are behaving correctly, right? So certainly if peers do not behave correctly and start feeding wrong information, then all of this would break. So certainly you would need a layer of security on top that is preventing that. And that again adds overheads. So that's something to consider as well. Okay, so let's do this question and then we can take a short break. So this is asking you about BitTorrent. So it's asking you, what does BitTorrent use tit for tat? Yep, most of you are correct. This is to decide who to upload to, right? Remember when you're downloading, looks like people are changing their answers. when you're downloading, we go by the rarest first logic, right? Whereas when you're uploading, you need to decide which of these peers am I uploading to, and then we try to say, okay, you amongst my peer neighbors, these are the peers that were giving me chunks at a very high rate. So I'll select them and I'll upload chunks that you're requesting, right? So the correct answer is indeed this third one. So yeah, well done. Okay, so let's take a break. And while we are at break, in fact, one of you uploaded a nice, Justin uploaded a nice XKCD comic. So I'll put that here. I also have a meme. So maybe I'll show you the meme first. It's an easy one. You'll hear a lot of these protocol jokes in the rest of this course. And then I'll show the other one, which is also nice. And let's take a break. I'll stop the recording just for a couple of minutes and then we'll come back. Yeah, one thing I should also mention is the stuff on DHT is not in the current version of the text. So what I've done is permission from the authors. We do make this available for you here, right? So if you need to read it up, you can certainly look it up here. There's a question. Yeah, that's a fair point about the routing. So here the assumption is we forward queries in the clockwise direction. Certainly you could imagine a protocol where you're also sending queries in both directions, and then that way you could sort of, if you're querying for things that are closer this way, you could imagine an routing algorithm that does that. Certainly, yeah, that's a fair point. But I think I noted here that in these slides, we are assuming queries only go in the clockwise direction, right? It comes down to simplicity, right? So the more complexity you add, the extra effort that the nodes need to do. So it's always a trade-off in designing things like this. But yeah, fair point. Okay, so yeah, there's a point about node may not necessarily know which direction is closer. Yeah, so you'll have to, I mean, you can, if you do want to design a scheme like that, you will have to think of certain considerations like that, right? So I think it typically you just go with keeping things simple, as it's called. So try to simplify things as much as possible, with as a result of which you might take some performance hits, right? So that's the trade-off as a network designer that you always need to consider. Okay, so let's now move on to something different, and this has to do with how content is distributed. And particularly, even though we'll focus on video, I mean, the same concepts kind of apply to general content as well. But obviously, since video makes up a lot of traffic, I mean, you'll see all sorts of statistics. Like here, for example, you see that 80% of the residential ISP traffic in 2020 was due to video streaming services, right? So video makes up a huge chunk of the data that we exchange over the internet. So that's the reason we kind of talk about video here. And at the same time, we'll also look at the actual mechanisms in which video files are actually transferred over the internet. So of course, the challenge here is to ensure scale, right? Because really we are talking of billions of users, right? A lot, I mean, how many subscribers to some of these services have? How many people watch YouTube videos? We are really actually talking of billions of users. So obviously, in order to deal with scale, we cannot use centralized concepts. That would never work. So we certainly need ways to manage scale. And the other challenge is also heterogeneity, right? Because viewers may be connected through different networks. Some may be on low bandwidth networks. Some may be watching stuff on different form factor devices like mobile phones and stuff like that. So there's all that consideration to also think about. So the way CDNs are managed essentially are through distributed mechanisms, and a lot of this is done at the application level. So just a few slides about general video concepts, so that you have a bit of appreciation for what is actually entailed when we talk of video streaming. So what exactly is video? Well, it's nothing but a sequence of images that are played at a very fast rate, right? So 30 frames per second. You might have heard of terms like 30 frames per second or 60 frames per second. So that's basically the rate at which these images are refreshed. And as humans, we cannot actually see that these are actually images. We think of it as a continuous video, but in practice, it's not. It's just images being sort of shown at a very high rate, right? And then if you look at each image itself, it's an array of pixels, and each pixel is represented by certain bits, which sort of indicate the color and perhaps intensity and other information that's needed to render the actual image that you're seeing. Now, one thing video relies a lot on is redundancy, right? That is actually very crucial when it comes to transmitting video, because you'll see that in a lot of scenes, things do not change across these frames, right? So here you're seeing a person actually running. So this is frame I, this is frame I plus 1. So if you visually just compare, there's only a slight difference, right, from between the two images. A lot of this background is pretty much the same, and you even have redundancy within a certain image itself. So if you look at just this image by itself, all of this part here is very likely the same color, right? So there's a lot of similar color there. So you can save a lot of information by not repeating all of this in the top part, right? Part here, and so on and so forth. So you can exploit redundancy, as it's called, spatially within one image. And you can also leverage redundancy across multiple frames. So imagine you have sent information about this frame. So when you're sending information about the next frame, you don't necessarily have to send the entire frame. You can only send the difference, right? And then the program that's interpreting that can look at the previous frame, and based on that can interpolate and figure out what this next frame is. So a lot of these video coding algorithms, they exploit both spatial and temporal redundancy a lot. And that allows them to reduce the amount of data that's being sent, because in the end, the more data you send, the higher bandwidth you're using, right? So there are various ways to encode this. So CBR is effectively a constant bit rate video, which is just encoded at a fixed rate. This is not very popular because this doesn't allow us to exploit the spatial and temporal redundancy. So typically, most videos these days use variable bit rate, right? So in scenes that are sort of where you have a lot of this, you can exploit it. In some action sequences and stuff like that, you may not be able to exploit a lot if the image itself is very busy, and then things are changing rapidly across multiple frames. So in those instances, you might actually be sending a lot more information for those parts of the video, right? So some examples you'll see are of encoding are noted here. MPEG-4 is a very popular one that's used for streaming over the internet, right? And this is the sort of simple scenario. So you have the video. Remember, here we are talking of streaming pre-recorded content, right? Live, if you're talking of streaming something live, like this lecture, most of these concepts apply, but then the other issue there is the actual content is not sort of stored. So you can't prefetch a lot of information like you can here. So that's the additional constraint when it comes to live streaming versus streaming of stored content, right? So you have the video content stored, you have a client that's downloading this over the internet. Now the challenge is the bandwidth can vary, and even the latency can vary, right? It will depend on, I mean, things like how congested is the internet. And it also depends on different parts of the network, right? So if there are other users in your own house that are using the internet, if there's congestion in the ISP, if there's congestion in the core, if there's congestion at the server itself, right? So a lot of these factors come into play, and all of this can vary at a very small time granularity, right? And these are the issues that will hamper your video performance. So the way things work are, for simplicity here, we are just assuming like uh, this is sort of showing you the data as it's being sent, recorded essentially. So let's say videos are recorded at 30 frames per second, they're stored, and then the server starts to send the video out, right? And then here essentially is where the video is received and played out by the client, right? So this is the delay. And in this particular slide, we are just assuming the delay is fixed. So you'll notice that once the server starts sending, the packets arrive back to back essentially without any variation in the delay. Now in practice, if things were like this, it would be very simple to design video streaming applications if the delay was actually fixed. In practice, the delays are actually variable, right? And what happens with streaming content is the player here, the client, will buffer a certain amount of video and will start playing them at a slightly later time. So it doesn't necessarily start playing immediately. It waits for a while. So it has a few packets stored, and then it starts to play back, right? In the hope that once it starts playing, all the remaining part of the video will arrive in time to be played out. If the buffer empties out, then we have a problem. Then you might have noticed this happening. I'm pretty sure every one of us has had some experience where the video essentially freezes, right? That's because the client side buffer has just run out. There's no more data to be played, and it's just waiting for the next part of the video to arrive from the server, right? So ideally, we certainly want continuous playback. Too many such buffering incidents are not desired when watching videos, right? And of course, there are other challenges like the client itself might change, right? So most video clients these days allow us to sort of move anywhere, right? Essentially within. So you might suddenly fast forward, you might pause, you might rewind, and that also needs to be accounted for. So the streaming application should adapt very quickly to that. And the other issue is the packets themselves, as we have seen, they may be lost. And as you'll see later when we talk about TCP, TCP uses retransmissions to deal with potential packet loss, right? And this can actually be problematic in video because, I mean, to some extent, you may benefit from retransmissions, but sometimes the retransmissions may arrive too late, right? The person watching the video may have already moved forward, and then some old retransmission arrives at the client, which is practically useless because the video has progressed beyond that point. So all these sort of things complicate the way video applications are run on the internet. So in practice, this delay is actually variable, right? So here again, to keep things simple, we are assuming a constant bitrate transmission. In practice, this may not be so smooth because most practical video streaming happens over variable bitrate. But in any case, so here you notice the delays are actually variable, right? So they keep changing from packet to packet. So let's say the client waits for a certain duration of time and starts playing out the video. So this is the amount of data that the client has buffered. And now the hope is that it will never run out of buffer. I mean, there'll always be something buffered. So even if the delay varies, there'll at least be something in the buffer for the client to maintain this playout that is at started. Because at any time, if this buffer runs out, then the client will have to pause and the video freezes, right? Now, in terms of the actual protocol that's used for transferring a video, these days video transmission largely happens over HTTP, simply because there's a lot of infrastructure already in place for uploading web objects. So the idea being, why not just leverage of all the web infrastructure? And that's the reason pretty much most video streaming clients these days use HTTP. Now there are variants of this, but effectively the most widely used version is what's called dynamic adaptive streaming over HTTP, which in short is referred to as Dash. There are slight variants, like Apple has its own slightly different variant. I think they call it HLS, HTTP live streaming. I mean, in concept, it is very similar. There are some nuances that might be different, but the general concept is fairly similar. So the idea there is the server actually breaks up the video into multiple chunks. And in effect, each chunk is actually encoded at different rates. So you can imagine different qualities of the videos are actually maintained, right? In fact, if you go to YouTube or any sort of typical web streaming application, you'll see that sometimes you can actually choose the quality of the video. You can also set it to auto, which is actually the default effectively, which is what we'll look at in the next slide. So each video is effectively recorded in different qualities and then broken down into smaller chunks. So effectively for each chunk, you will have different qualities. So imagine low, medium, high, right? Just for the sake of this discussion. And then since all those chunks are transferred over HTTP, there is what's referred to as a manifest file. So the first time you hit play, you want to watch a video, the first thing that happens is your browser goes, or the client that's essentially streaming that video will go and fetch what's called a manifest file. So this file will contain the URLs for all the different chunks. And then the client has to decide which chunk it needs to go and fetch, right? So each chunk is then sort of fetched one after the other. The client also incorporates certain intelligence whereby it measures the server to client bandwidth, so the current download rate that it's experiencing. It also monitors the current buffer. So the client will also have a buffer where all the video packets are being stored. So it will keep checking the current occupancy of the buffer. It will keep measuring the current download rate. And based on that, it can then select the appropriate quality. So if it sees it has sufficient video to play out, if it sees the download rate is very high, it may start choosing chunks of the highest quality. If at a certain point it observes the buffer is running out and the download rate is also poor, it may select the lowest quality, right? So in fact, the quality of your video may change depending on the dynamics in the network, right? So imagine, just for the sake of simplicity, we have 3 different qualities. So as you see here, and then of course the current bandwidth that you experience will also keep changing with time. And then down here, you see how the various chunks are being played out. So initially, the first 2 chunks were of the lowest quality. Then perhaps the client intelligence saw that, okay, we could actually go higher because we have enough things in the buffer, the bandwidth is high. So you notice we move up because the bandwidth is high here. And then here we notice a drop, so we drop back down, right? So you can sort of observe this behavior over time, where the actual qualities of the chunks may keep changing, right? So this is the general idea. Of course, the specifics can vary a little bit depending on the particular vendor implementation, right, of these protocols. Okay, so that's about streaming. The next thing to look at is the actual distribution, right? So this is where CDNs come into play, right? So now the question is, okay, we know that we need to go and fetch chunks. We need to specify the URL, but then how do the actual, so this will again be a host name, right? So some host name. So how does that host name get mapped to an IP address effectively? So that's taken care of by the CDN networks. And again, as we discussed here, we can't just rely on a single server. So the normal practice is to store multiple replicas of all the videos across a very large geographically distributed network of CDN. Now there are Of course, companies like Netflix and stuff, they manage their own CDNs, but there are other CDN providers like Akamai, Limelight, who make a business out of it, right? So if you are a content provider and you do not want to yourself manage your own CDN network, you can pay Akamai some money and then they'll take over the distribution of your content. Now, again, there's a lot of specifics here and we won't be getting into all of that. I'll just give you a very high level view. And there are two broad ways to do this. So there's this one notion of what's called enter deep. So the idea there being you push the CDN servers as deep into the access networks as possible. So get them as close to the users. And this is what companies like Akamai do. So in fact, these numbers are already very old. These numbers would have grown exponentially by now. So Akamai has actually embedded a lot of their servers directly into the local ISPs. So it's very likely that whatever ISP, local ISP you're connected on, it's very likely that that is actually hosting some Akamai servers within the ISP network itself, right? So that way, content that you're requesting from Akamai can actually serve it directly from those servers. So very close to you. The other option is to not go that deep, but to still be as close as possible. So this is, if you remember, we talked of this IXPs, Internet Exchange Points. And in fact, I showed you some information about an IXP in one of the earlier lectures. And you saw that that IXP had was connected to all the typical content providers like Facebook, Amazon, Netflix, and so on and so forth, right? So this bring home idea is to not go directly within the access networks, but be just maybe one hop away from the access networks, right? So this is something that's used by Limelight, and sometimes some companies could also use a bit of both. Google, for example, uses both these ideas within their own CDN network, right? So let's look at a very simple example. So let's imagine we are talking of one particular Netflix show, let's just say Mad Men or whatever is your favorite one. So Netflix would actually deploy multiple copies across all their servers, right? And then when someone is requesting for a copy, they would need to be directed to the CDN that's closest to them, right? So it sends the query, say, to the Netflix front end. Netflix provides them with that manifest file that I mentioned, which has all the URLs. And now the question is, where should the user be directed to, right? And normally this is, you're directed to what is considered to be geographically closest to you. Of course, they may be using other heuristics. So necessarily being geographically close may not always be good, because what if this path is highly congested, right? So in that case, you might benefit from another server, which may be just one hop away, but which may be on a less congested path. So most of these streaming providers will use all these sorts of heuristics where they may actually measure the current level of congestion, and based on that, they may redirect you to a different server, right? So yeah, most of them would be using some of these heuristics. So you might have heard of the term over the top. So this is what's often referred to, this whole notion of distributing content, because you're kind of doing this on top of the internet using all sorts of heuristics, servers, and all sorts of measurements that they're doing here, right? So some of the challenges essentially are, I mean, everything is fine as long as the network is not congested. Once the network is congested, then we have issues as to how do we deal with that, right? So some of the things we need to deal with is which CDN node should a client be directed to? The viewer behavior may also change when they experience congestion. They may suddenly stop watching stuff. So we want to be appreciative of that. And then the question also is, how do we place the content? I mean, you can't virtually, Netflix cannot store every video that it has on every server, right? That would mean they would have to replicate, I don't know, zetabits, whatever, of content all across, right? So certainly that's not feasible. So of course, most of the popular content would be replicated everywhere. But then the question is, how are they determining popularity? Again, that depends on regions, and so on and so forth. So there's a lot of heuristics involved here on determining all of this, right? Let me just go through some questions here. So how do we know what content to fill on those servers? So yeah, that is a challenge, as I mentioned, right? I mean, it's easy. So you'll always have like a small percent of the content will be watched by a lot of users. So that is very easy. So most of the popular Netflix shows, sure, you replicate them everywhere. But then what about the ones that are not so popular, right? So these are, I mean, I don't have a good answer to that. We need to working for some of these CDs to figure out some of these specific heuristics, right? I'm sure they're doing all sorts. A lot of this, I guess, depends on the geography. So certain shows are more popular in certain parts of the world. So obviously that can be something that could be used. And of course, they could do it based on user behavior as well, right? So let's say suddenly if some people in a region start watching a new show, and let's say that was not originally replicated, and Netflix observes that more people are watching it, then it may, based on the current demand, it may start sending more replicas, right? So they do all these sorts of measurements, observations, and based on that, they design certain heuristics. I think that takes care of the other question about content being the same. So again, popular content is the same, but then otherwise things keep changing all the time, right? POP stands for point of presence. Let's say you can see Australia top 10. Is that statistic or market? Well, I can't tell you exactly what Netflix does. I mean, they are not going to reveal everything they do, right? So we kind of have to make some assumptions there. I'm sure, I mean, I'm pretty sure most of these content providers are constantly keeping track of all this, right? And in general, yeah, whatever they show us is probably a bit of marketing. They may not necessarily reveal all the intelligent things they do, right? Because there's always competition between these providers. So let's look at how DNS plays a role, right? Earlier we had talked about how DNS plays a role in the context of CDN. So let's look at an example of that. So here I'm not using any real applications. These are all made up names, but you could kind of map this to any real service. So let's say Bob is requesting a particular video as shown here, right? netcinema.com, whatever. And let's say that's the front end. Now, most of these providers would host their front end on AWS or something like that, but they may manage their own CDNs. So the front end might be hosted at AWS, but then the actual content is stored on their own CDN networks. So here we are saying NetCinema, let's say it's managing its own front end, right? And then it's outsourced all the video storing to a CDN company called King CDN. And let's say Bob is requesting the file. This is Bob's local DNS server, right? So firstly, Bob is trying to get that particular file. So that's the URL. So it sends a query to map this to an IP address to its local DNS server. I've skipped the steps. So I mean, you could imagine Bob's local DNS server may first contact the root, may first contact the TLD and so on, but we've skipped over that. Let's just assume Bob's local DNS server knows the authoritative name server for NetCinema, right? So it requests for that particular file. Now, since the content is not stored here, the content is stored in King CDN. So this would actually return a CNAME, right? We remember we talked about how CNAME can be used for redirection, and this CNAME will redirect to that particular domain, as you see there, kingcdn.com/whatever, right? Now to resolve this, Bob's local DNS server would then need to contact the King CDN server. So that would be this step 4 that you see here, right? And again, imagine Bob's local DNS server knows the authoritative DNS server for King CDN. So based on that, it can get the actual IP address. And now what King CDN, the authoritative name server, could do is it could actually check where Bob is located, right? So it could look for Bob's IP address. It sees that Bob is in Australia. So it could redirect Bob to the Australian kingcdn.com server. If this request was coming from someone in Asia, it could redirect it to an Asian CDN server, and so on and so forth, right? So this is where the location information of where Bob is could actually be useful, right? And then Bob could go and fetch content from there. I mean, what even sometimes these CDN providers may also do is they may do some measurements along these paths. So if there are multiple options, if there are multiple servers, and they have these measurement sort of agents you may think of deployed in the network, they may see this is coming from a particular ISP, and this ISP has, say, delay X to this server, it has delay Y to another server, and it may then choose a server that has lower delay. So all these heuristics sort of come into play here in figuring out which is the best CDN that your CDN server that your query should be directed to. Right? Are authoritative DNS servers distributed to? I mean, they will be replicated. They may not necessarily, I mean, it depends, right? They probably are distributed in some global scale as well, but definitely not at the level as the actual content servers, right? So certainly we need replicas for DNS servers, but only a few, whereas you would have hundreds of replicas for the content server. Which step does it know where the client's request is coming from? Here, so the query comes from Bob's local DNS server, right? Again, here the assumption is this is in the same network. Now, if Bob's is using a DNS server that's not within its ISP, again, there we have a problem, because let's say Bob is using Google's local DNS server. In that case, the query is not coming from Bob's IP, it's coming from here. And then this may not necessarily always work, right? So you could have issues like that. Would the authoritative DNS consider load on the CDN servers when determining the IP? Yeah, that's actually what I just hinted, right? Most of these CDN providers would be doing some sorts of measurements within the networks as well to sort of get a sense for how much loaded the CDN servers are, how much is the expected latency between the requesting ISP and their servers. So it may not purely just be based on geography. Some of these other things may also come into play, right? Does the CDN DNS server use a low TTL value because the optimal CDN server may change? Yeah, that's also a good point, right? So remember, that said, it probably, because each, remember we talked about each chunk being different. So you need to do this on a chunk by chunk level anyway, right? So, but you're right, yeah. If you have remembered which server you were directed to, the next request you may send directly to that server. So I think, yeah, they also use low values in the TTL, right? The TTL for the actual DNS records. So they can do all these sort of, they can use all those sort of knobs essentially to tune how best to redirect you to what they think is the best place. Now, again, remember, these are all heuristics. There's no oracle that knows exactly everything in the network, right? So they try their best essentially. Is there a database that maps globally unique IP addresses to physical locations? Yeah, that's a good question. So generally, yes, as we'll see later, there is, based on your IP address, you can get a rough idea of where you're located. Again, it's not always exact, but roughly, yes, you do come to know roughly that, say you're based in Sydney. You can even drill down sometimes to the specific suburbs, but again, not always 100%, but you do get a reasonable idea, right? And then with Netflix, again, things are kind of similar, except Netflix is managing its own CDN networks. It does host the front end in AWS. So that initial query that you send when you're trying to watch something will be sent to AWS. But then once you get the manifest file, you're actually going to be fetching content from the Netflix servers themselves. And Netflix is pretty aggressive. They've actually deployed a lot of their own servers directly into many local ISPs, right? So that allows them to service the clients with minimal delays, right? And again, they're using all sorts of heuristics to figure out which content to push into these servers and so on and so forth. Yeah, so the goal here was just to give you a sort of high-level view into all of this. I mean, we could spend lectures and lectures going over all these specific heuristics, but we certainly don't have time to do that here. Okay, so let's look at this question now. So this is kind of asking you, what role does the authoritative DNS server play in the context of CDN? There's a question, is ISP part of a CDN? No, I wouldn't. I mean, ISP is providing you with the service, right? It's a CDN is a different beast. There's the role of a CDN is to provide content. The role of the ISP is to provide connectivity. So those are two distinct things. CDN providers often embed their servers within ISPs. So they have some sort of relationship, right? I don't know exactly what sort of monetary relationship they have in order to host that. Right? Yeah, so what I meant when I said that was Netflix has installed their servers, CDN servers within ISPs. So they tell your ISP, hey, take this server, put it in your network, and this will be exclusively for Netflix content. We will manage how the content is stored there and so on and so forth. And the ISP also benefits, right? Because if they can service clients directly from servers within their network, that keeps their clients happy, and they don't have to then pay a higher tier ISP to go and fetch that video from somewhere else. So it's a win-win for Netflix and a win for the ISP as well. Yep, this is correct. So it's basically to map the query for each CDN object to the CDN server closest to the request. Again, closest here we mean little loosely, as I already indicated this. The best and what is best can change. It may simply be closest, or it may be the least loaded. It may be the server that gives you the lowest latency, and so on and so forth. Is the content provider the same term as CDN? It depends. I mean, in the context of Netflix, yes, because they are producing the content and they are their own CDN. When you talk of an organization like Akamai, then Akamai is the CDN, and companies that are paying Akamai to host their content are the actual entities that create the content, right? So if I set up my own content service, I may pay Akamai, say, hey, go and be my CDN. I'm going to give you content. It's your responsibility to distribute it to everywhere, right? Okay. Okay, so let me I might go a little over today, guys, because I just need to wrap up the socket programming stuff. Certainly feel free to jump off if you've got other stuff. I may only go over, say, 5 minutes or so. So I want to sort of quickly conclude with a discussion on socket programming. And earlier we talked about how when we are writing applications, we are writing pieces of code that run on the end systems. And then when we actually run those programs, we effectively have processes on these end systems that are trying to communicate to each other. And we treat the socket as a door through which these processes can exchange messages with each other, right? And as an application designer, you have control over this. You have very minimal control over this, what's behind. You can select a few settings, but all of this is really managed by the OS. And that makes it very easy for us to write applications, because all we really care about is writing our programs and then using the appropriate socket API calls. And then the OS effectively, and the internet, of course, takes care of the rest, right? So we really have two choices here, UDP and TCP. So let's start by looking at UDP first. UDP is very simple in that the API it gives you, the service that it gives you is effectively, it tries its best to deliver packets, but it doesn't guarantee. So it effectively gives us unreliable transfer of groups of bytes, which we call datagrams, between the client and server, right? So that's the abstraction that UDP presents. So there's no notion of a connection, no notion of handshaking, anything like that. I mean, if you need to do that, you could do that within your application. UDP doesn't do any handshaking, right? So when you're using UDP, all you do is from in your program, you create these UDP segments, you provide the destination address, IP address and port number, and then you send that UDP datagram and hope that it reaches the other side, right? When the receiver receives this, the receiver will then look at the header information. It will figure out who sent this. So the sender side IP address, sender side port number, it can extract that. Then depending on what your program is doing, it will perform that service. And then typically some reply will get sent back, right? So that reply gets sent back to this IP address and port number that's extracted from the received packet. Now, here, remember, I talk of client being the sender, server being the receiver, but of course, both endpoints are sending data to each other, right? Now, do remember when you're using UDP, packets may be lost or received out of order. So it's up to your program then to deal with that. It's not UDP's responsibility, because when you chose to use UDP, you were made aware that this is the abstraction. So if you're not happy with this abstraction, or if packets do get lost, then it's up to you. By you, I mean, when you're writing your application, you need to deal with that, right? So if you look at the pseudocode, the UDP client programs are typically fairly straightforward. So you would create the socket, and then you would, so this is the client side socket, essentially the socket that's used by the client for communication. And then normally what you would do is you would have this sort of loop where you send a UDP datagram to the server port and IP address, then simply wait. You expect a reply to come back. Again, depending on exactly how your program is expected to work, but this would be the normal thing, right? You send a request to the server should respond back. Then you look at the actual packet, depending on what your application is doing. And then you may need to go back and keep doing this a few times. And depending on whatever is the end condition for this loop, at some point you'll exit the loop and then close the socket, right? The server also creates a socket. So that's the server side socket. It binds to that port and then it keeps waiting, essentially, right? The server is then waiting for the clients to send information to it. And normally you would again have some sort of loop. The server normally just is alive forever, right? That's the normal convention. The server receives a UDP datagram from a particular client. It needs to record the information about the client, the IP address and port number, so that it knows where to send the response. Then depending on what service it's providing, it will do the action, create the actual response message, and then send the datagram back, right? And keep doing this. And eventually when you want to kill the server, you sort of close the packet, right? So yeah, this is just making the point that the server needs to remember where it needs to send the response back to, right? So there's a question. What's a common use for UDP? DNS is a very common use for UDP, right? DNS uses UDP. There are various other applications that may use UDP, which are very simple sort of request response applications. Wonder why it needs to extract the port. So this port information is for the other side, right? So if you go back to this picture, so the server is here. The server has received something, right? A UDP datagram. Now it needs to know where it should send this back, right? So it's the information about the client that the server needs to extract so that it knows where to send the message back to. This information was already provided to the client, right? So the client doesn't, I mean, that's something you tell the client that, hey, this is the port and IP address of the server. But from the server's perspective, it's just waiting. So one client sends it something, so it needs to know where it should send this back to, right? Does the connection keep alive? There is no concept of a connection here, right? In UDP, there is no connection, basically, right? The reply port may be different to the port it received on. Well, I think people often get confused with this. So here we are talking of this port is the client port, right? This port is the server port, right? So this port has no relationship with this port, right? So the server is listening on this port. It receives a message. Now, when it's sending back a response, who should it send it to? Because there could be multiple clients who are contacting the same server, right? If you talk of a DNS server, let's say this is a root server. This root server may receive DNS queries from multiple clients. So when it receives a query, let's say it's created a response. Now it needs to know where it should send this information to, right? So what it needs to do is when it receives a UDP datagram, it needs to figure out where this message came from. So it needs to record the IP address and port number of the client that sent it the query so it can send back the response, right? So if you send multiple requests, how do you tell which response goes with which request? So that's exactly part of your design, right? So your application has to do that. It's not UDP's responsibility to do that. So in your application program, you need to write code that will manage all these multiple clients because it's not UDP's responsibility. UDP has only opened up this port and it's only going to send and receive datagrams. So if your application needs to keep track of all these separate requests, then you need to write code in your application to do that. The server is not listening on multiple ports. So I'll talk a bit more about all this in a couple of weeks, but the server is just listening on one single port here, right? Okay, so moving on now to TCP. So TCP is actually very different. TCP gives you the abstraction of a byte stream, right? So TCP is completely different to UDP. TCP has the notion of a connection. So what happens is the server sort of opens a socket and says, hey, I'm ready to accept connections. Then the client will contact the server, say, hey, I want to set up a connection with you. At which point, assuming the server wants to go ahead with that connection, a actual connection gets established between the two endpoints. And then it's as if a pipe has been established. Then the client and server simply keep feeding each other bytes of data. So the abstraction TCP actually gives is a byte stream, right? So the client first contacts the server. So the client needs to specify the port number of the server, the IP address of the server. And at that point, a connection request gets sent, assuming the client is happy, the server is happy to set up the connection. It will then create a new socket for communicating with this process. And effectively, this allows the TCP server to set up multiple connections because normally, for example, if you're a web server, you'll want to talk to multiple clients, right? You can't have a web server only servicing one client. That no one will want to use your web server if you do that. So you want to be able to talk to multiple clients at the same time. So TCP allows this very easily by creating a new socket effectively to talk to each client. And we'll talk about exactly how a TCP socket is uniquely identified. So some of this may seem a bit confusing at this moment. I'll go over all of this in much more detail when we get into the transport protocol. But effectively, the abstraction here is a byte stream. So once that connection is set up, you're actually reading and writing bytes. So this, when you write TCP programs, they are very different from programs that use UDP. So that's the abstraction. You do use, the server sets up what's called a welcoming socket. A connection request comes in. The server, assuming it's willing, sets up a new socket. And then here we have a connection between the client and the server, right? Now imagine a new client wants to talk to the server. So again, it sends a handshake message to the welcome socket. This, assuming the server is willing, it sets up a new socket here that's used to talk to this new client. So that's client 2, that's client 1, right? So this welcoming socket is effectively just like a door. So you knock on the welcoming socket, the server spawns a new socket where you set up a pipe, and then you're simply reading and writing bytes into this. What is the difference between TCP connection and socket? So all of this effectively is a TCP socket. So a TCP socket is uniquely identified by information about both these endpoints. So this whole thing effectively is your TCP socket. This whole thing is another TCP socket, right? So essentially it's a combination of the port number and IP address of this end and the port number and IP address of that end. Okay. So the pseudocode for a client would be like that. You create a socket and then you say, hey, I want to talk to that particular server. So you provide the IP address and port number of the other side. Then the client will go and do the handshake. Assuming the server is willing, a connection socket will be established. And then the client is simply reading and writing data into that socket. And once it's done, it closes the socket. The server would create that welcome socket. It would sort of bind to that and say, hey, I'm now listening on that welcome socket. And then it effectively goes into a loop. So it then waits for a new connection to come in. It accepts that connection and then reads and writes data into that connection, closes the connection, and then goes back. Now, mind you, if you write a program like this, at any given time, you can only talk to one client. Because once you have set up this connection, your program is sort of stuck here, reading and writing data into the socket. So if a new request comes in, you won't be able to service this, right? So this pseudocode only applies to a server, which can only manage one client at a time. Obviously, you want to have something that can deal with multiple clients, because in this model, if any new request comes in, it's just going to sit waiting for a new connection socket. So almost all servers would have some concurrency built into it, right? And the very typical way to do that is to use multi-threading. So what you would do is you would have your main thread, which is doing this effectively. And then when you spawn a new socket, you create a separate thread. And then you essentially have this thread communicate with one particular client, which means if a new connection requests arrive, you can spawn off another thread. So effectively, you spawn off as many threads as the clients that are trying to talk to that server. Right? So that's allows us to build some concurrency. Right? Questions. When will we look at the handshake process? We'll look at the handshake process when we talk about TCP. I think that would be in week 5. So not the next week, but the week after. And we'll go over all of this again in a lot more detail. In lab 2, do we need to write a UDP client? Yes, your lab 2 is asking you to write a UDP client, exactly. I'm not sure what you mean by inaccurate. You might post this question on the forum. I'm not sure what you mean by inaccurate here. How do clients know where to find your welcome socket? So yeah, when you, for example, HTTP, right? So if I'm hosting a HTTP server, I've told you my port number. I mean, by default, that port number is 80, right? Because we assume HTTP uses 80. And I've told you my IP address, right? Which you have got through a DNS query effectively, right? So now your client knows my IP address, it knows my port number. So that's what it tries to connect to. Right? If you're using a non-standard server for which port numbers are not known, then you will have to tell that application that, hey, I'm using this particular port number. So all standard applications use well-known port numbers, which are already known. Right? The client does, yeah. So all web, I mean, if you talk of HTTPS, it's 443, but if it's just plain HTTP, it's assumed that the server is always listening on port 80. That's the default assumption for all web servers. Similarly, for SMTP, it's 25 and so on and so forth. So port numbers are well known for all servers, right? Okay, I think we have run a little longer than expected. So I think that pretty much concludes the application part. So in fact, next week, we'll directly start getting into the transport layer. We'll start off with some basics and then start looking at UDP and TCP. Right. So have a great week. Make sure you're working towards your second lab, and your assignment spec will come out next week. It's almost ready, but I'll wait till next week just to have another read and fix up any inconsistencies, and you should see it out by Tuesday next week. So have a great week, and I'll see you all next week. Bye-bye.